Hello and welcome to the 12th lecture. We will be talking about the chain rule. Okay, so this is the following rule. So we're first going to state it, then we'll explain why it's train pitches, and then we'll do many examples practicing it. So given f and g, so I'll take the simplest case, the differentiable or whatever in the whole line, differentiable everywhere. So I'll state a more precise theorem, a more general theorem after this one, towards the end. So they're differentiable everywhere, and we want to consider the composed function, which is f composed with g. Then the derivative of composed function is this. It's the derivative of f at g of x times g prime of x. Okay. All right, so this is the chain rule. Why is it true? Okay, let us draw some pictures. Let us draw the graph of g, whatever it is. Okay. Well, actually, why not make that the graph of f, because that's more important. Let's make this the graph of g. G is some function like this, and what we've got f composed with g. So think of this as being some kind of production line, factory production line. We have two machines. We have the first machine, which is g. So we take our x, we put it through g, out comes g of x, and we put it directly into the new machine, f. And then we get f of g of x. Okay? So we take our x, act on it with g, and then it goes into f, like this. All right, so what are we considering? We're considering the derivative, right? So what do we've got? We're going to work with the definition. We're going to be considering this limit as h goes to 0 of f of g of x plus h over h. And what we've learned about differentiability, and we know that g is differentiable, is the following, that g of x plus h minus g of x over h is incredibly close to g prime of x, and it gets closer and closer as h tends to 0. So multiplying by h, we have that x plus h. This is a lot like g prime h, and the error here of this difference is very small, much smaller than h. And I'm going to write that, or represent that, by writing plus minus little order of h, like this, which means that we have a tiny error, but the error is a lot smaller than h, and that's important. That'll be important going forward, because everything we do will be working on a scale of h, and we are going to use the fact that g of x plus h minus g of x is pretty much like this, and there's an error, but that error is tiny compared to h, and it's so tiny compared to h that it's not important for the discussion we're having. But the fact that it's way smaller than h is important, so I'm going to write that down. Where h, so I'm going to write like this, is a lot smaller than h, and the smaller h gets, the more this little order of h is smaller than h. Okay. All right, so let's start this. We first have to take our x plus h and our x, put it in the first machine. This says x. This is x plus h. And the first machine, g, sends us to here. This will be g of x. And this thing here would be g of x plus h. Cool. Now we go put it into the second machine. So here we have g of x. And this thing here will be g of x plus h. Okay? And then this is being sent to f of g of x, and this is being sent to f of g of x plus h. Okay, first thing to note is that this gap here is g of x plus h minus g of x, which, as we've discussed, is incredibly close to just being g prime of x times h and then a tiny error of order size h. But everything we're doing will be of order size h. These pictures we're drawing are of order size h. So a tiny, tiny error, which is way, way smaller than h, is not visible on this picture, right? So if I were to replace this g of x plus h with g of x plus g prime of x plus h, I would be so close to this that I couldn't see the difference, given that this is at the size order scale h, right? Because, again, the difference between this thing and g of x plus g prime of x is way, way smaller than h. So I can write this like this. Well, maybe I'm going to overcrowd this. And I'm going to overcrowd this picture. Okay, well, let's just try and squeeze it in. So this is really close to g of x plus g prime of x times h. And there's a tiny, tiny error, but it's so small compared to h, we don't see it on this diagram. So this distance right here is kind of like g prime of x times h. That's the gap between the two. And again, not quite, there's a tiny error, but it's so much smaller than h, we can't see it on the picture. Cool. All right, so let's look at this. This thing, because again, g of x plus h is incredibly close to g of x plus g prime of x times h, this thing is incredibly close to being f of g of x plus g prime of x times h. And it's not quite this, but again, the order of error is a lot smaller than h, so it's practically indistinguishable. We can't see it at this scale. Cool. So when we write that, then what are we doing? We're trying to compare this gap here, which is the difference between g of x plus h, or start again, of f of g of x plus h minus g of x minus f of g of x, right? That's this gap here, right? And we're dividing it by h. And what our picture shows is that if we do this kind of triangle like this, this thing here is g prime of x times h. So this slope here, what is it? This slope here is, where should I put it? Over here. This slope is like f of g of x plus g prime of x times h minus f of g of x over g prime of h, right? Yeah? Because that's the height divided by how far along we're going. And for very small h, this is an awful lot like just g prime of g of x. Yeah? Because as h goes to 0, x is just some fixed number, then this is exactly the definition of differentiability. Yeah? Cool. So that kind of gives us a hint of how to go, because the thing we're trying to understand is this thing divided by h. And we have a very similar expression here. So we actually have that f of g of x plus h minus f of g of x over h is incredibly close to, and more close to as h goes down to 0, f of g of x plus g prime x times h minus f of g of x. And let's write this as g prime of x times h, and then let's put a g prime of x right here. Yeah? So the g prime of x's from top and bottom will cancel, and we get almost this thing, except this guy is replaced by g of x plus g prime x times h, because again, that's what we know from this thing. Yeah? Cool. So in the limit, call this thing star. The limit as h goes to 0. I just called it star and then I forgot to use it. Let's call it star and use that. Star is equal to the limit of this expression as we go to 0. And this g prime of x, it's not moving with respect to h, we can just pull it out, right? G prime of x, the limit as h goes to 0 of f of g of x plus g prime of x over h, g of x over g prime of x times h. And again, we've talked about this before, this thing is really a lot like this, and in fact the limit as h goes to 0, it really is exactly f prime at g of x, which is equal to f prime of g of x times g prime of x. And that is our formula. Okay, so this, as with all these other theorems we've discussed, is not a mystery. It's not a big surprise. It's not very unnatural. It just follows from looking at this quantity, okay, and trying to understand it in terms of pictures with the realization that g of x plus h is morally, for this purposes, we can just treat it like g of x plus g prime of x times h, because the difference between these is way smaller than h, and we're doing everything at the scale of order h. So any error that is way smaller than h, when we're dividing through by h, it just vanishes, right? We only care about things of order h. So, perhaps it's a bit more involved than some of the other pictures we've drawn, but it is nevertheless just pictures. And I could have skipped these pictures and just done some algebraic manipulations like this. But I wanted to show you how we get to this, why we would naturally guess this if we just carefully looked at what happens when we consider an expression like this and divide it by h. Yeah? Cool. All right, so that's our formula. Not a very difficult formula. And with this, we can differentiate a whole bunch of stuff. So, first thing. It's example 1. Let's take f of x equals the square root of x squared plus 1. So, many of you have done calculus before, probably used the chain rule before. If you haven't done it for a while, if you've never done it, I recommend you warm up by carefully thinking about the pieces of your composed function, writing out the outer function and the inner function. We're going to make the convention that the outer function is f, little f, the inner function is little g. Write out their derivatives and then put in the pieces. So the first, whatever 3, 4, whatever 7 examples you do of this, write out the pieces and make sure you get it right. And then once you're getting it consistently right, then you don't have to do that. But don't try and just do this in your head, missing every possible step you can put in. I fairly often hear from students who say, I watched the class and it seemed reasonable and I tried to do it myself and I couldn't do it at all and I don't know what went wrong. And they are not doing it systematically, trying to do each little bit that they're sure of one bit at a time. They're trying to do it just in kind of one go, and they're getting it wrong. And they're not. If you do break it up into little pieces and then you get it wrong, you can trace back and see which little piece you got wrong. If you just don't do that, if you just try and do it in big jumps, then you can be completely confused. So that's the point of this language, that we have our understanding, our intuition, our pictures, and then we can express them very, very carefully in arbitrarily precise detail, putting in all the little steps of thought so that we can see that they're all valid. And if something goes wrong, we can see where something is wrong. It's kind of like a bit like debugging a piece of code, right? If something's wrong in your code, then what do? You try and identify which part is going wrong. So you'll, remove some part of the code, see if it runs then. And then if it runs, go, okay, the part I removed clearly has the problem there, and you'll narrow it down and narrow it down. But unless you had the whole code written out and you could just look at each piece of it step by step, you wouldn't be able to do it. So that's why we do this. That's why we carefully break it down. So if you're having difficulty just even getting started with some new topic like this, then just break it down into the small pieces one by one. Let's do it. So, outer function. Maybe a good idea for you to pause the video and think for yourself, what is the outer function? See if you can come up with it. The outer function is just the square root. And then the inner function is x squared plus 1. Let's find out the derivative. So if we differentiate the outer function, what do we get? We get 1 over 2 x to the minus 1 over 2. If we differentiate the inner function, we just get 2x. Now, we put in our formula. Let's do everything, do every possible step. I'm going to write f prime of g of x, g prime of x. Now let's put in bit by bit what we have there. So we know that f prime is given by this. So it's 1 over 2 g of x minus 1 over 2, and then g prime of x. Now we can put in g prime of x, which is 2x. Yeah? Now finally let's put in what g of x is. That's 1 over 2, 1 plus x squared minus 1 over 2 times 2x. X over square root of 1 plus x squared. And that's it. That's it. All right, so we could not have put in more steps. We've put in every step, and we've made the littlest jump from here to here to here to here. Do it this way to begin with. Make sure you're getting it right doing it this way, and then learn to do it faster. All right, we're going to raise the board, and we'll do some more examples. Okay, example 2. We have y of x is equal to sine of x squared, and then b, we have y of x equals sine x squared. Okay. So, solution. Okay, this time we're not going to write out explicitly the inner and outer function. We are just going to look at it. So, the outer function for a is the sine function, and the inner function is the x squared, right? So, we know that y prime of x is the derivative of the outer function applied to the inner function. The outer function derivative is cosine. Multiplied by the derivative of the inner function is x, so the derivative is 2x, and that's it. That's A and B. The outer function now is x squared, and the inner function is sine. So we differentiate the outer function, we get 2x. So y prime of x will be 2 sine of x, because we're going to apply sine of x, the inner function, to the derivative of the outer function, which is 2x. Yeah? Multiplied by the derivative of the inner function. And the inner function, the derivative is cosine. Because the inner function is sine, so the derivative is cosine. Yeah? Okay. Not too bad. Let's do another one. Example 3. Y of x is equal to x squared minus 1 power 100. The outer function is x to the 100. The inner function is x squared minus 1. So differentiate the outer function, it's going to be 100 x to the 99. So apply that to the inner function. We have 100 x squared minus 1 to the 99. Differentiate the inner function, we differentiate x squared minus 1, it's just 2x. If you want, clean this up, 200 x squared minus 1 to the 99. Okay, not bad. Let's do another one. Example 4. Get over here. Change colors. Y of x is equal to x squared plus x plus 1 over 3. Solution. What's the outer function? The outer function is x to the power 1 over 3. And the inner function is x squared plus x plus 1, right? If we differentiate the outer function, we're going to have a third x to the minus 2 over 3, right? So let's take the derivative of the outer function, which is a third, and then apply it to the inner function. So a third x squared plus x plus 1 to the minus 2 over 3. That's the derivative of the outer function applied to the inner function. Now we differentiate the inner function, and we're just going to get 2x plus 1. And that's it. If you want to clean that up a little bit, it's going to be 2x plus 1 over 3x squared plus x plus 1 to the 2 over 3. And that's it. Cool. Let's do this one. Example 5. Y of t is equal to t minus 2 over 2t plus 1 to the power 9. All right. Now we're getting to a little bit harder problem, because the inner function is this rational function which we're going to have to apply the quotient rule to differentiate. So we're going to have to put some algorithms together here. But all we have to do is just take it step by step and not get intimidated, okay? Because it's just putting pieces together. So this is saying, how do you eat an elephant? You eat it one mouthful at a time, or one bite at a time. This isn't exactly an elephant, but this is like whatever. This is a little bit bigger than these little mice that we've been eating. Let's say this is I can't think of a medium-sized mammal we want to eat. What do we eat? Okay, I don't want to say it's a pig. This is a sheep. This is a sheep. We're going to eat it one mouthful at a time. So we differentiate the outer function first of all and apply it to the inner function. So t is 9 2t plus 1. That's our first mouthful. And if you're in any doubt, just put in extra steps. So let's write the derivative of the inner function rather than trying to do it in one step. So if things go wrong, we can trace back and see what we did bit by bit. And then we can say to ourselves, okay, the first step was definitely correct. Okay, now let's build from this. 9. Okay, and now we're going to differentiate this thing. We apply the quotient rule. So now this is just an application of the quotient rule, which we've practiced lots of times. We know how to do. We just do this. So everything over the bottom, guys, squared. Differentiate the top, leave the bottom alone. If we differentiate the top, we just get 1. So we're going to get just 2t plus 1. And then minus, leave the top alone, and differentiate the bottom. If we differentiate the bottom, we just get 2. It's 2. Okay? And then let's clean that expression up. So if we look at this, we're going to have 2t from this and 2t from this, and they will cancel out. We'll have a 1, and then minus 2 times 2, which is plus 4. So on the top, we're going to have 5, right? And then we're going to have this t minus 2 to the power 8, and then times 9. So 4 times 5, start again, 9 times 5 is 45. So on the top, we're going to have 45 t minus 2 to the 8. And on the bottom, we have this 2t plus 1 to the power 8, and then this 2t plus 1 to the power 2, so it's going to be 2t plus 1 power 10, and that's it. Cool. All right. Let's do another example. Now, things get a bit trickier. So, example 7. Y of x equals e to the sine of x. It maybe looks a bit trickier, but I claim this is still the same kind of game. The outer function is e to the x, the inner function is sine. So we differentiate the outer function, we get e to the x again. We apply it to the inner function, we just have e to the x times sine of x. Now we have to differentiate the inner function. Derivative of sine is cosine. So it's this. Okay. All good. Let's do this guy. Example 9. We have y of x is e to the sec of 3x. This is a bit trickier because now we've got these 3 functions. We have 3 functions composed with each other. The innermost function is this guy. The second innermost function is sec, and the outer function is e. So again, just break it down into little pieces that you know how to do. So, differentiate this. The derivative of the outer function applied to the inner function first of all. The derivative of the outer function is e, and the inner function is sec of 3x, so we get sec of 3x. And now I would write this just so that you have it as some step that you know you have to do. Okay? Then we do this step. And now we have another chain rule to apply. The inner function is 3x, and the outer function is sec. We know the derivative of the outer function is sec tan, so this whole thing will be e to the sec of 3x sec of 3x tan of 3x. And now we differentiate the inner function here, which is just this 3x, and the derivative is 3. Let's put the 3 right here. Okay, same thing. We just break it up. One mouthful at a time. All right. Let's talk about how the chain rule gives us the quotient rule. So quotient rule I couldn't explain to you in pictures. It was too complicated to do it directly. But it does follow from the chain rule. So we change color. Oops. If we try and differentiate the quotient of 2 functions, then that is like doing a product rule to the function f and the function 1 over g. 1 over g is the composition of 2 functions. the outer function is 1 over x and the inner function is g. So we can write that as f prime of x, differentiate the first guy, leave the second guy alone, plus leave the first guy alone, and let's write what we're about to do. Differentiate the second guy, which is 1 over g of x. Yeah? And again, 1 over g of x, just the composition of two functions, outer function 1 over x, inner function g. So that is f prime of x over g of x plus f of x. If we differentiate the outer function, we're going to get minus x to the minus 2. We apply the inner function to that. Right? I hope that's clear. So let me put it over here. So 1 over g of x is g of x to the minus 1, so that when we differentiate it, it's going to be minus g of x to the minus 2, and then we have to differentiate the inner function, which is g of x. So we're going to have a minus here. It's going to be over g of x squared, and then we have a g prime of x, differentiating the inner function from this composition here. And then we give ourselves a common denominator, and we have exactly the chain rule. We have g of x, f prime of x, minus f of x, g prime of x, over g prime of x squared. And it's a very good idea for you to do this a few times, just in case you panic and you start to worry that you don't remember the question rule. Yeah? If you do this, then you will be able to be for sure, you'll be sure about what the question rule is, no matter what the situation. Okay, cool. So, what other cool stuff can we do with the chain rule? Well, remember how we talked about that when we consider this function b to the x, then it has this really nice property that the derivative of b to the x was just a constant times b to the x, and we found the b so that that constant was 1. Yeah? Well, the chain rule now allows us to calculate exactly what the derivative of b to the x is, what that constant is, by this simple trick. So, if we want to figure out what b to the x is, right, we know that e and log are the inverses to each other. Right? They're invertible functions, they both satisfy the horizontal line test, and they are the inverses to each other. Log is defined to be the inverse of e. Right? So we can write this as e of log, actually let me write natural log with ln, because that's, maybe, should I do that? Yeah, let me do that. E of log of x to the x, right? And then our knowledge of algebra tells us this is just this. Cool. Oh, I messed it up. This is not x, this is b. And this is b. Yeah, once again, because e to the log b is just b. Cool. And we're differentiating this back to x, so now we have the composition of two functions. The outer function is e to the x, and the inner function is x times b to the x. So when we want to differentiate this thing, it's just differentiating this. So differentiate the outer function, apply it to the inner function, we just get this thing again. And when we differentiate the inner function, we just get log of b. Yeah? And then this thing, as we know, is just equal to b to the x. So we get log of b, b to the x. Yeah? Cool. And if this is right, this should recover what we know, that e to the x when we differentiate is e to the x, because this is just the more general thing where b is an arbitrary number. So when b equals e, we should get what we get before, and sure enough we do, because log of the number e is equal to 1. Yeah? So if b equals e, then log of e is 1, and that's it. That gives us what we had before. So this now gives us the ability to differentiate b to the x as easily as we can differentiate e to the x. we just have to remember to put this log of b in front. And you could sort of backwards engineer that it was going to be log of b, because it has to be something that when we stick in b is equal to e, it comes to 1. And of course log has that property. So it's not a surprise, this formula, but again, better to be able to work it out. And the only thing you need to work it out is just to remember to write b of x as e to log b. And in fact, that's a very useful trick. Whenever you have anything to some power, it's always better to write it as e to log of that thing to the power, and then put that power around the outside, this, rather than deal with it itself. So this is a very useful trick to do. Once again, you have something to a power, then write it as e log of the thing, and then that thing to the power. Because then you're ending up differentiating e to the x, which you have no problem doing. So with this, we can do examples of differentiating b to the x, and there are some examples you'll be doing in your web assign, and it's exactly the same as all of this other type stuff. Simply practice it. The only thing you need from this particular section is to get the formula right. So look at the explanation, convince yourself of the formula, and if you want to, you can just avoid looking at the pictures I drew, and just look at it as an algebraic expression like this. Like this. And simply replace this g of x plus h with g of x plus g prime of x times h. So the point of the pictures was to inform us that that's the way we want to look at it. And once you do this one step, then it's not much of a jump to go, okay, well then I can understand that by just writing this. And then this thing here, I know is just going to tend to the derivative of f at g of x, because this is just some small thing that's going down to 0, right? So we can just write h tilde is equal to g prime of x times h. And as h goes to 0, h tilde goes to 0. So this expression here is f of g of x plus h tilde minus f of g of x over h tilde times g prime of x. And then h tilde is going to 0, so therefore this is going to our formula. So really not very hard to get this formula right. So once you've got the formula right, then practice it. It's an algorithm, break it down step by step, and you'll find that you can do this. This isn't hard. So that's what you have to learn for this particular section. Okay, that's enough for today. Have a great day.